Probabilities. Ya. Thomas Augustin es profesor de la Universidad de Múnich, en Alemania. Él es el jefe del grupo Fundamentos de la Estadística y decano de estudio de los programas de licenciatura y maestría en Estadística y Ciencia de Datos. Thomas tiene un diploma y un doctorado en Estadística de la LMU y ha trabajado en la LMU y en la Universidad de Bielefeld antes de convertirse en profesor de la LMU en el año 2003. Sus principales intereses en investigación están relacionados con los fundamentos de la estadística y ciencia de datos, incluyendo probabilidades con incertidumbre, modelos con error de medición generalizado, clasificación bajo incertidumbre compleja, teoría de la decisión e historia del pensamiento estadístico. También está interesado en gestión de calidad de datos en investigación social empírica y estadística oficial. Él nos va a hablar hoy de su charla, tiene el título Towards Reliable Modeling and Learning Under Complex Uncertainty. Welcome, Thomas.
Okay, thank you very much for the introduction, for the kind invitation. I'm quite happy to be with you. And yeah, it's a great honor to be able to present something here. Title of my talk was already announced, so I will look at some aspects of modeling and learning under complex uncertainty. So I will just jump around between some topics I have done together with colleagues and PhD students in the last years. So to give you an overview, if you are interested in some details, of course, I'm happy to share further material with you. Please also feel free to contact me if you like to have the slides. So at some points in the slides, I put also references and such things to make the slides a little bit more self-contained. So if you like to have them, I'm very happy to share them with you. So, as I said, it's work with the joint with a lot of people I like to pay credit to. Here is a table of contents. I will start with a little bit of, so to say, ideology, why I'm interested in these things, motivation and background. One technical device I will use are imprecise probabilities. And I will try to give you some very informal idea about this. So for many statisticians, it's quite a strange topic. And so I think I should introduce them. A very informal understanding of this stuff is really sufficient. Then I will look at frequentist statistics and Bayesian statistics a little bit. And then I will look on imprecise observations. So when we discuss what would be current methodological challenges in the area between statistics, data science, machine learning, etc., I think we all agree that it's important to have interpretable, explainable methods, also in machine learning and artificial intelligence. And I know that also in your group, there has been a lot of interesting work in that direction. I think another challenge would be to go more directly into decision theory. I won't speak a lot about this, but I think if the discussion touches this point, we could also discuss this. Also, I think we should start to become even again more aware also of limits and contingencies of the methods we use, at least in the political area. There is a big hype about data science and artificial intelligence, and people expect more from us than we can deliver. And I think it's also kind of scientific responsibility to say what does not work. And a special part of this is, I think, a careful reflection and communication of all kinds of uncertainty. Uncertainty, of course, is a work statisticians like. So statistics basically is about uncertainty. So we calculate p-values, we calculate confidence intervals, credibility intervals, etc., to cope with uncertainty. But statisticians too often forget that they are typically only looking at sampling uncertainty, an uncertainty which vanishes with increasing sample size. And there is another thing like one what could call big data uncertainty, complex uncertainty. I typically use this term. So kinds of uncertainty that do not vanish with increasing sample size. So when we have some complex data, deficient data, or better non-idealized data, then we have this kind of uncertainty. And I think there is surprisingly little work in statistics to handle these things in a proper way. So the slides is basically, if we are honest, we have something like a big spinning of different deficiencies. We have measurement error, misclassification, we have rounding, we have response effects due to heaping, etc., etc. Many data are anonymized before we can analyze them, and so much things more. So basically, we should be I'm sorry, the slides do not always react as I wanted them to be. So this is also a kind of uncertainty. But with the spinning of deficiency in mind, we should basically remember that not always what we see is actually what we want to see as data and is about what we want to learn. So there is, going back to Carnap, this scheme where we have basically ideal, so to say, variables, and we want to learn about this ideal level, but our data just come from somehow different variables, mismeasured error, mismeasured variables, variables with classification error, etc., etc. And of course, the art is to make inference not just on the relationship between these data we can observe, but on the relationship between the ideal level in the background. Statisticians typically do this by modeling the deficiency process. So we make models about this relationship to make a step back, or we characterize situations where the deficiency may be ignored. So for instance, missing at random is such an assumption, but typically we need very restrictive assumptions to come up with a precise solution. For instance, in measurement error, you need a lot of additional knowledge. You have to know the type of the error distribution. You need a lot of independence assumption, etc., etc. You have to know the moments of the error distribution and many things more. So you basically can come up with a precise solution, but the question is how credible is this precise solution given the big amount of assumptions you have to put into this. So there is this law by Charles Mansky, an econometrician who is becoming more and more popular, at least in econometrics.
We lost.
Sorry, that your slides are not showing.
I wanted just to communicate.
Oh,
okay.
Okay.
I thought it's too boring to have just the slides. So Charles Mansky, he stresses that statistical learning, or also machine learning, if you want, it has another dimension. It has a dimension of credibility. And this credibility is directly directed to practical relevance. So if we have models which need some very strong assumptions, they are basically mathematically fine, but they are no longer credible. So the credibility of inferences decreases with the strength of assumptions maintained. This is Minsky's idea, and he has built a theory in econometrics. It's called partial identification around this theory or around this paradigm. And much of what is done there also has an influence on the following slides. So I was happy to cite Minsky. So we should not just have precise solutions by the price to have precise solutions if then nobody agrees or believes in these solutions. In artificial intelligence, so the first artificial intelligence wave representing uncertain knowledge, there is some development in computer science where statistics and probability theory is left with the idea that probability is a concept which is too inflexible. So the connection between uncertainty and probability is challenged. Clear writes, one of the big names at that area, by theories which are demonstrably capable of characterizing situations under uncertainty. So it became clear that there are several distinct types of uncertainty, that this is what they realized, that uncertainty is a multidimensional concept, and that multidimensional nature of uncertainty was obscured when uncertainty was conceived solely in terms of probability. So this is, from another point of view, an appeal to think a little bit about more complex models for uncertainty, which can take into account a multidimensional understanding of uncertainty. At least from this point of view, standard statistical models, one would say, require a level of precision and internal consistency of the information that is very rarely satisfied in practice. So that's basically the major point here. I think we need a statistical and learning methodology that takes into account quality of information properly. So the classical statistical model has a precise solution if we have good data, and it has a precise solution as well if we have very messy data. And that's something which, to some extent at least, has a negative effect on the credibility of the statistical results of the learning learning endeavor. So basically there are two things which will be considered further on. Imprecise probabilistic models, which often are named imprecise probabilities, which is under advertising aspects a very unfortunate misnomer. How can you call models which claim to be better models, how can you call them imprecise? But that's the starting point of the whole theory with a book called Imprecise Probabilities, and though this name was retained, although it led to a lot of misunderstandings, and we have some attempt to try to estimate imprecise models. Mathematically, this means that we look basically at a set of traditional statistical models. With the idea that we have, so to say, small sets, although this is mathematically a wrong expression, then we have high information. If we have large sets, then we have little information. And so we can have this on the probability side or on the learning on the statistical side. So later on I will discuss data imprecision and model imprecision, and both will be captured by sets of models. And I will show you that imprecision somehow helps to robustify certain situations, but it also is a very vivid modeling tool as a step further. Okay, now I will have a little look at imprecise probabilities. Except you have some questions or comments. So Leo said, and I like this very much, that it's customs with you that you just ask questions when they pop up, and I think it's a very good idea. So interrupt me at any time, for instance, now. New question at the moment? Yes.
Well, I might have, I'm not sure if it's the right question at this point, but I mean, people talk about, I don't know, fuzzy logic, fuzzy values, I mean, or is that the kind of things that you are?
I would say it's somehow related with the aim to have a more generalized modeling. But fuzzy sets typically generalize the notion of a set, while we, or probabilistically of an event, while we try to generalize the notion of probability. That's, of course, it's basically similar to some, well, there could be a similar motivation. Mathematically, different things happen, so to say.
Okay.
Yeah, I also had just a comment because you mentioned, Thomas, that there is a sampling error, for example. But at the same time, I think even if you have a census, you still may have imprecise data, even in the census, not just sampling.
I completely agree. So I think that's basically the point, that so uncertainty should not be limited to the samples. It's a big error. Many statisticians too. Of course, we all know that good example of census data, they typically have quite some imprecision in it, some measurement error. It's difficult to collect, etc. That's basically a major point here. Okay. So thank you. Then I will try to continue. As I said, imprecise probabilities, just in a nutshell, so to say. So we have the idea to provide a more general concept of probabilities. There are some foundations in terms of axiomizations. The most famous one is given by Peter Woolley in a book in 30 years ago now, in 1991. Yeah, and I just wanted to say that basically I will build on a very intuitive understanding. So think for the moment just of imprecise probabilities as a set of traditional probabilities. So instead of a single probability, you think that the correct model is a set of classical models. If you have good data, if you have good information.
We lost him. Maybe we should.
Voy a mandarle un mensaje.
Yo le mandé recién por aquí mismo, eso sí. Se salió y se volverá a meter, supongo.
Sí, yo creo. Le mandé un mensaje en todo caso ya, pero si se salió, pues probable que se haya salido él. Yeah, no, now we're fine.
So, sorry, I don't know why, but yeah, probably I should not speak about imprecise probabilities.
It's a sign.
Okay, so coming back, probably where I was interrupted. So we have these sets of traditional probabilities. They have also tradition in artificial intelligence. It's very easy to model ordinal probabilities. We just say it's less likely than something else, or partial assessments, etc. And also in statistics, it's used quite often. And I would like to mention quickly, so first application, if you want. We all know this, what I like to call the mantra of statistical modeling. So many people also say that imprecise probabilities are just an unnecessary complication. Of course, every modeling has some imprecision, but that's the idea of models. So people say essentially all models are wrong, but as we all know, some are useful, as Box says. But I would be also like to stress that maybe also some are dangerous, because if you think that it does not matter whether you take this model or another model which is looking similar, then you implicitly assume that you have continuity in your conclusions. And that's something which is, I think, dangerous. Here you see two distributions. So I know that you also have a colleague who is working on heavy tail distributions. You, of course, know this example. So you have a normal distribution and the so-called Cauchy distribution. The densities are extremely similar. So I think with poor eye, you probably would not distinguish whether data can come from the one distribution or from the other. But statistically, this has dramatically consequences. If you look at the sample mean, then under normal distribution, the sample mean is again normal with a decreasing variance. Of course, we know this. Under Cauchy distribution, it's also again Cauchy distributed, but the scale parameter does not depend on n. That means in the first setting, you have the basic idea, as everywhere in statistics, that if you take means, you can learn about your data or the mechanism behind your data. So taking the mean gives you an information about the mean of the data. And the more data you have, the more precise you are. While in the second case, your conclusions are irrespective of the sample size. Whether you have one observation, 100 observations, thousands of observations, you never can do better. And that's something which goes basically against the basic idea of statistics and learning. And you see this happens just when you take the Cauchy instead of the normal distribution. So it's by no means the case that, so to say, models do not matter whether we take the one or one close to it. There are situations where this is highly discontinuous. You cannot learn from data in these situations. And that's very strange. It was the basis of one direction of imprecise probabilities, which is closely related to robust statistics. So the idea was to look at so-called neighborhood models. So instead of taking a precise statistical model, like a normal distribution, you say you assume that the data are approximately normal and make a mathematical model with an appropriate topology that formalizes this, that you have a distribution which is somehow close to the normal distribution. And then such paradoxes do not occur anymore, that you have completely different learning behavior, for instance, of the sample mean. This theory around, so in the addition of the so-called Huber-Strassen result, you can extend this to many statistical models. If you like, we can discuss this later on. And the idea to use neighborhoods could also be of interest in machine learning. If you have classification trees and you build neighborhoods, that basically would be as a mean against overfitting. So by taking the data you have seen as a kind of imprecise, it helps you to avoid overfitting.
May I ask a question? I mean, the outcome of the first bullet here will be a classification tree as usual, right? So in terms of application of the classification model, there is no difference. The difference is how you compute basically the branching out points and etc. How you branch out in the yeah, right? And that
Exactly,
is based on this new proof concept. So may I ask? I mean, I am intrigued by the possible connection that there should be between the imprecise probabilities and, on the other side, entropy in the classical sense. Is there anything like a correspondence between entropy in the classical sense and uncertainty from your point of view? Something like a mapping from one to the others. Since entropy somehow measures uncertainty, I mean,
it sounds quite natural. And some people also tried to do this, basically to look for a connection, basically in the area of belief functions. I think that still, if you look at entropy, you have this, so to say, precise, you're looking for, so to say, a precise model of uncertainty. Probably one would need something like a generalized entropy. And that's basically what also happens in this classification trees. So you look at the kind of interval valued entropy, and by working with this interval valued entropy, you get this stabilized classification trees.
Okay. So, just very quickly, so there is something like a theory or definition of entropy based on the imprecise probabilities.
The bad thing is there is not one definition, there are too many.
Okay.
So if you introduce entropy axiomatically, you can take the axioms and play a little bit around with them, and depending on which axiom you generalize, you get different concepts of entropy, generalized entropy. That's so to say the bad thing here. But of course there is a very natural connection. Further question?
So basically, your neighborhood models are in the family of the original models? So
you can construct it in different ways. So you could just take a family of normal distributions. It helps for some applications. Of course, if you think you have different tails, you typically also take not just one parametric family, but you use one, so to say, distribution as a central distribution, and you look at all distributions in a certain neighborhood, around this distribution neighborhood in a topological sense. So for instance, if you use the Prokhorov metric, it gives you a very convenient model. And then you have distributions of a similar shape, but they are not normal distributions, but somehow similar. And that's the way which is more often used, because then it helps a little bit against outliers. If you take just a set of normal distributions, you're again very sensitive to outliers.
all right. Thanks.
Okay, so thanks again. And I continue with, so these neighborhood models were mainly used in frequent statistics. Of course, there is also Bayesian statistics, and there is also some aspects of imprecise probabilities in Bayesian statistics, which can be mentioned. I just need some notation. You all know this. Bayesian inference, some people say it's a natural way of learning. So we update the prior distribution in the context of data to obtain posterior distribution. This updating is done by this Bayes rule, which gives the whole theory its names. Of course, you can formulate something like a generalized Bayes rule. Take sets of distributions, update them element by element, and you get a set of posterior distributions, which can also be described by a lower and upper posterior distribution. What are these things good for? They allow, at least to some extent, modeling of ignorance. As you know, in Bayesian statistics, you have this notion of non-informative distributions. And again, similar to these generalized entropies, you don't have a single concept of non-informative distributions, but you have conflicting concepts, which basically comes from the effect that even a non-informative distribution does contain information. And so if you take basically the set of all probability distributions on a certain space, then you can model something like ignorance much more realistically. Another point I would make is, and I would make this in a little bit more of detail, classical Bayesian methods, I would say, are not able to distinguish between variability and indeterminism, which I would like to demonstrate by what is called prior data conflict. So if we run convenient Bayesian models are more conjugate models on canonical exponential families. So I have written down here the formulas, just if somebody would like later on to look at the slides, so don't look too much on the details here. We all know that the updating works like a weighted mean between prior and sample. So we have weights, we have this prior guess of the mean, and we have the sample, and we just take an average. Such informative priors are well known to transform information, to use information. But the big question is what to do if if the information we used in the beginning, so if our prior information and our sample are conflicting. So you assume the mean to be 5 and you observe 6. Say the weights are 50-50, so you get 5.5 as the mean. You also could have assumed the sample is minus 10, and the observation is sample mean is 20. You can get something which gives you just a weighted value, and it could be the same. And unfortunately, in Bayesian statistics, the variance is not does not depend on the sample. So you could have completely different situations, but you get the same result for the posterior. So prior fits well to the sample, you get a certain distribution, and you could get the same distribution if the prior is completely away from what you observed in the sample. And since the posterior distribution should contain all information, it's a little bit iffy. And Bayesians have developed some kind of goodness of fit things, but I think IP can very nicely help. If you use sets of distribution, you come up with something like here. It's demonstrated by sets of distribution functions. So you start with a set of distribution functions, lower and upper distribution functions described, and you observe something which is in accordance with your prior. Then you get a posterior which becomes smaller. However, if you observe something which is completely in contrast to what you have assumed, then you get a very huge set of posterior distributions, basically telling you that you should not make any conclusion. You should be very careful with decision making. And I think that's something which is quite attractive, because it allows us to have a warning in this Bayesian learning process. If we assume, so to say, a wrong prior, then we get warned if the sample is in conflict to this prior, and we need very many data to again give the whole weight to the sample. But for a small data sets, we are just warned to make any concrete conclusions. And I think that's something which is very attractive. We're just currently trying with some people from medical statistics to use this in their context. Okay, this was a quick look at Bayesian statistics. Do you have further questions?
Yeah, I have a question. I'm intrigued by how you choose your family of distributions, I mean, or an interval, because, well, when you are looking for just one distribution, you know there is only one, good or bad. But here in this case, how do you restrict your interval or your family?
I think there are certain assessments procedures which suggest certain intervals, and then if not, it's always at least as good as assuming one. And of course, you could do some kind of sensitivity analysis in the sense that you say, how big could the set be such that the conclusions I take from it are still stable? And that's something which is, for instance, the people from medical statistics are interested in this. So if you have conclusions which are stable, or which are stable just if you assume one single prior distribution, and if you go a little bit away from it, you get different results. You probably should be careful. While when it's stable on the very big intervals, then you are basically fine with your conclusions.
Okay,
you don't look very happy.
No, I assume there are some methodologies that you can apply.
There are some assessment procedures, of course.
To determine what is the best, at least a starting point, and maybe just a set that you might prune at some point, or an interval that you can shrink or something like that. I don't know.
There are procedures to assign this. You also could use the same idea from before to have neighborhood models with a certain radius. So for instance, the radius can be interpreted as the amount of data you think, the percentage of data you think they could behave somehow strangely. If you think you have a well-behaving setting with 1% of the observations somehow erroneous, you take a parameter of 1%. If you think your observations are 10% of your observations may be somehow misleading, you take this to 10%. This is construction by epsilon contamination models, which is a quite convenient way to assess prior distributions also.
Okay, thank you.
Okay. Yeah, so it's 45 minutes, or I have spoken about 40 minutes. You said we should aim at 1 hour. So I just would look at some further ideas of imprecise data, maybe 7-8 minutes, and then we could have further questions. Would this be okay?
Sounds great.
Okay, so when we look at so we have imprecise models, and now we look at imprecise data. Basically, there is something when we have imprecise data, then basically we observe data not in the granularity in which we originally intended to do this. So we have subsets of the intended sample space, but there is a quite nice distinction, which is also very important. It goes back to Couso and Dubois. We have to distinguish whether we observe something precise, whether we have imprecise observations of something which is precise, or whether we have some precise observation of something imprecise. Since the time is running, I try to explain it just here. So both things, for instance, occur in election polls. So in Germany, we have a multi-party system, and basically also the seats in the parliament are given by the proportional to the number of votes. And so it's quite interesting all over Germany which party gets how much votes. But in pre-election polls, many people are undecided. So it's becoming more and more. Maybe I also show you a slide on this. Yeah. And so many are still undecided, but typically they are just undecided between 2 or 3 parties, which also may form a coalition later on in the parliament. And now you can apply both points of view. If you think of this as an, so to say, precise observation of something imprecise, you think that people who are undecided between party A and B, for instance, the Christian and the liberals, they are an entity of their own. They're different from those who vote for the Christians, and they are different for those who vote for the liberals. That's, so to say, this ontic point of view. And I will continue with this in a minute. Or you could also see it as in the sense of forecasting. You just know that those people who are undecided between 2 parties, they will vote for one of the 2 parties. So you have imprecise observation of something precise, namely a precise vote. If you take the first point of view, this ontic point, where you take this as sets of their own, you have basically a statistical situation that you go from one sample space to another one, and basically you go from so to say, a set of parties, you just go to the power set. So you have a strange sigma field here, the power set of the power set. And yeah, but basically this is still, so to say, just a probability space. And that's very convenient, because if you do analysis, you just can apply standard models from voting research to the situation of imprecise data, ontically imprecise data, and you get indeed something which shows you that it makes sense to take this combination of certain parties as entities of their own. They have a different constitution as the single parties. So this is something which is very convenient. You just can take any statistical modeling procedure or any machine learning procedure. We used also classification trees and random forest in this context. You can take to analyze this data once you have transformed, so to say, the sample space. For the case where you have imprecise observations in the sense of some precise truths, this of course happens very often. You have these undecided voters, but it's also a way to handle missing data. It occurs in data protection. You could have similar problems when you merge data sets with partially overlapping categories, etc., etc. And so I would more or less conclude with this. This is from a big survey in Germany. They tried to cope with undecided refusing respondents in a very special questionnaire technique. So people are asked about the income, and those who are refusing this question, they are asked whether they would be kind enough to give at least bounds, so whether they earn less than €1,000 per month or more than €1,000. And you can imagine how it continues. If respondents are willing to do this, they are asked further questions, and so it's tried to narrow this down. But basically, you also get imprecise data just from this complex survey scheme. With this setting, we have developed a profile likelihood approach, so a kind of imprecise likelihood approach, which helps to transfer statistical regression models, logistic regression, multinomial regression, and ordinal multinomial regression to such settings. I will quickly jump over this and come to the conclusions. Yeah, I tried to make some advertising for the idea that we should take all kinds of uncertainty into account, and we should do this properly. So not just look at the sample uncertainty, which vanishes with increasing sample size, but because that there are very many situations where we have this uncertainty from censuses to surveys, where the errors do not vanish with increasing sample size. And I've heard that I think we need a statistical methodology, learning methodology that takes into account this, takes into account the quality of information. And yeah, I try this by referring to Mansky's law of decreasing credibility. I said that we try to make reliable use of the information, basically by set-valued analysis, working with imprecise data as they are, not assuming them to be precise, but imprecise as they are, by using imprecise models. And from a practical point of view, this is often still sufficient. We get the answers in the subject matter context we need to get. And yeah, one can also use imposition actively in modeling, as we showed with, for instance, prior data conflict setting. That was a quick tour through some recent research we did. As I said, I'm happy to share the slides if they are somehow welcome. And yeah, I'm looking forward to your questions. Thanks you for your attention.
Many thanks, Thomas, for your presentation. Any questions? Any further questions?
I have a question. Yeah, first of all, thanks a lot, Tamar. It was a very interesting presentation. Actually, I am interested in the slides, so I will ask them by email, and I can share it, them with whoever wants them to take a look at them. But yeah, I mean, my question goes in the direction of something that you mentioned briefly about missing values. Yeah. So I guess that is an interesting area of application of your ideas. So there is recent work by Judah Pearl and Mohan on the formalization of missingness mechanisms in the style of Donald Rubin, right? As causal networks. Actually, for many purposes, you can use just Bayesian networks. So I wonder if there could be some use for your ideas, your theory in the context of, let's say, more generally in terms of causality analysis, causal networks, Bayesian networks, and if in particular that would give some additional light on the problem of dealing with missing values.
I agree. So the paper by Pearl and Mohan, I think it's really an extremely interesting paper. Yeah. So I'm still fighting with it a little bit, but yeah. I think I'm in good company when one fights with publications written by Judah Pearl. They're typically very challenging. Yeah, it brings a new point of view. And of course, it helps a lot to understand causality. Still, of course, it's difficult with the missing data because you basically make assumptions about things you don't see and you cannot see. So I have announced a PhD project where a good student should look at imprecise probabilities techniques for Bayesian networks, whether they could be combined with these Pearl and Mohan techniques. Okay. But so I think it's a really extremely interesting paper. As I said, it gives a completely new view on this missingness concepts. And it's always, it's amazing that after 30 years of little and new Rubin, so something substantially new comes into play. Yeah, and we had the idea to combine this with work on Bayesian networks, but we still are in the very, 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 very beginning.
Yeah, well, yeah. By the way, I'm very much interested in the subject. I am trying to do research myself in that direction, so I would be happy to. If you can, we should talk about that. Yeah, definitely. Just maybe a quick question. I mean, I don't want to monopolize the conversation, but you mentioned the paper by Couso and Dubois. Dubois is one of the fathers of possibilistic logic, possibilistic theory. I'm not sure if in that paper that you mentioned of 2014, they use possibility theory or classic probability, but that brings me to the natural question as to whether there is some connection between these imprecise probabilities and possibilistic theory.
Yes, there is. So there is, from a technical point of view, it's just one step more general. So you can write every possibilistic distribution as a coherent imprecise probability model in terms of volley. Or you can write it as a special case of a belief function. Every belief function is a special case of coherent probabilities in terms of volley or also in terms of Weichselberger. So there is this very natural connection. Yeah.
Okay, thank you.
And basically, especially with imprecise data, I think starting with a possibilistic model is quite often a good thing to do, because it's not too complex model, and it's but it already captures a big part of the problem.
Okay, thank you.
Oh, that's...
Any other question?
Actually, I have one question. Just I was thinking of the example that Thomas showed that about the Cauchy distribution versus the normal distribution, and I was wondering if through the method that you are working on, you can in some way shed some light on how to distinguish between the two cases.
I think one thing would be to distinguish between both cases. That there, in this very special situation, there are some kind of goodness of fit tests which just look at the tails. So with many data, you could distinguish both distributions, but you really would need a very high sample size. My basic idea would be not to distinguish between them, but just take all these distributions into a set of distributions if you think they are good models. So I basically would not distinguish, but have catch-it-all models, so to say. So where you have think of the normal distribution as a possibility, you think of the Cauchy distribution as a possibility, you think of all mixtures between these two distributions as a possibility, etc. And develop, what has been done, the Huber-Strassen theory is basically a kind of minimax theory. So they have developed minimax, optimal minimax tests to distinguish between hypotheses which are described by such set of models. And based on these testing procedures, also estimating, interval estimation and also point estimation was developed. But to some extent, it's mainly a minimax approach.
Yeah, I mean, I see your point in terms of the what you mentioned about the robust approach. So in some way, you can combine both cases, and actually that happened also when, let's say, when you think of a student tree distribution, thinking of incorporating all the cases, the normal cases and the heavy tail cases in one, just in one setting, in one family.
Exactly. Yeah. And the Cauchy distribution is just the t-distribution that there is 1 degree of freedom.
Just one particular case. So
it's so to say strange case of the t-distribution.
So usually when you have a problem, you don't know whether you have precise data or precise or unprecise data, the two options, no precise observation with something precise or precise observation with something imprecise. So how do you treat both cases? Because in some cases you might know what is the precise side and what is the imprecise, but
I think there are some situations where you know that there is, at least to some extent, a precise value. For instance, in this example with the income question, there is really, of course, you can have this econometric model with permanent income, where you say that income is permanent income is, so to say, per se an imprecise or difficult to measure construct. But beside of this, you have the idea that the person, you ask, what was your income in the last month? That's a really precise value. And one sees in this example that imprecise data not just occur because people are sloppy in measurement, but they're just arising very naturally from these survey settings.
So, but the assumption is that you need to know.
I think it's yeah, and in the election part, for instance, you could argue for both. And I think both give you different substantive answers. If you think of these parties as entities of their own, for instance, in Germany we have a left-wing party and Green Party, and those who are undecided between the left and the Greens, they are really different, as our analysis shows, from those who are just supporting the Greens and those who are just supporting the left-wing party. At least with respect to certain aspects. So it, from political science point of view, it really makes sense to take this as a precise observation of something, if you want to say that's imprecise. We also are brave enough to try our method to forecast the next German election when the results on the election will be next autumn. Then we will see, but we hope by treating those who are undecided only between two parties, it's a very strong information. But up to now, and at least in Germany, in these surveys, this information is just thrown away. And I think one really gets rid of a big bias. The more so as you, for instance, you have people undecided between the Christians and the liberals, it is not unlikely that both parties will form a coalition in the German parliament. So you basically, those who are undecided are just a precise vote for this coalition. And that's all information which is wasted by the usual polls. And up to now, so about 1/3 of people, Germany voters, potential voters, say that they are undecided. So it's not just a small quantity, but really a big issue. And when we are successful, we will report the results.
Become famous. So, but how would that compare, for example, with the Nate Silver method of averaging many different methods and many different data sets, for example, try to predict elections?
I think in some ways it's maybe the idea again, I would say this a bit similar as with Spassi said. So maybe some of the motivations are very similar. But I think that still averaging is not the best way to cope with imposition. So I think one should really accept that the result could be something imprecise. It could be in certain situations, for instance, in case of prior data conflict, I don't know at the moment. The information is somehow conflicting and I need more data before I decide. I think that's something which per se is of certain value. And if you accept that this is of certain value, then also the situation when you can make a decision is of specific value, because then you are told that your results are strong enough to make a certain decision. It's not just by construction that you always come up with a certain decision, you always come up with a precise solution by default. But when you have a strong theory which also allows for no conclusion or for imprecise conclusion, if you then can say, oh, the situation is clear enough to make a very decisive conclusion when you're robust against many critics.
Thanks. Any other questions? No?
I only have one quick question with actually a comment about this idea of that you mentioned, Thomas, about that the number of assumptions that you made in building a model. So I think it's quite interesting that in some way you would like to penalize the model in terms of the number or of how strong are the assumptions that you are making.
Yeah, I agree. I like this statement by Mansky. And I think it's particularly true when you have assumptions that cannot be tested. So for instance, if you assume a normal distribution, at least if you have enough data, you can test whether the distribution is normal or not. When you assume missing at random, you cannot test it. There is no test whether you have missing at random or whether there is a missing not at random situation. Both give you, even if you have infinitely many data, can give you the same distribution. So you cannot distinguish between them. So it's basically a matter of mathematical convenience to make this assumption, but this assumption may have very strict consequences. So this is basically Minsky's idea. Or for instance, if you work with measurement error models, you don't see true data, but you assume that the measurement error is normally distributed. And then you correct your data. It's very complicated is the procedure. Yeah, but all your outcomes rely on this assumption that measurement error is normally distributed or quer distributed, whatever. And you cannot test it. Except you have validation data, of course, but typically you don't. And this is the thing where I have made this experience myself. So my postdoctoral thesis was on survival analysis and the measurement error, and I took the classical statistical measurement error modeling to correct survival models, Cox models, accelerated failure time models, and so on. And I was very happy to show my results to colleagues from the sociology department, because I thought they always have measurement error. They agreed that they always have measurement error, but they were not interested in my results at all, because they said, yeah, what you ask us to do is to do a very complicated procedure, which we have to program ourselves. To come up with results we also cannot trust, because we don't know whether your assumptions are true. So this is exactly this missing credibility to which Minsky refers.
Thank you.
All right. So if there are no more questions, we thank again. Leo, you want to say something?
No, I'm just going to ask you for the slides. I mean, if someone is interested in having them, you can contact me.
Thank you.
Yeah.
I am interested.
Okay. So, okay.
And this video also, it's available to anyone.
Okay. So you will put it on YouTube or?
What?
Oh.
On YouTube, yeah.
Do you put it, the video?
You want to have the video?
No,
where is it? Is it available at YouTube or?
Yes, they put it on in YouTube.
I will send you the link when it is up. Yeah, thanks a lot, Thomas. It was very interesting. Yeah,
So
we have
great pleasure to